So let's talk about the nature of sound. What are the characteristics of sound? How are sound waves created? And how is the speed of sound calculated? Now, sound is a longitudinal wave created by a vibrating object. Now, the object can be a string, it could be vocal cords, or it could be the diaphragm vibrating inside of an audio speaker. Sound can only be created or transmitted through a medium. Now, the medium has to be either a solid, liquid, or gas. Sound cannot exist in a vacuum, so there's no sound in outer space. Here I have an example of a drum laying on its side, and we know that if we strike a drum, it will vibrate in simple harmonic motion. It'll go back and forth. Now, that back and forth motion of the skin of the drum will push on air, on the air molecules. And what I have is a diagram of a section of the air. Now, what will happen as that skin gets pushed out during the vibration, I've exaggerated it here with the green line. So it pushes all the air particles and smooshes them all together. And consequently, the particles are said to condense because we are pushing them together. It's more dense. And we also call that a compression. So what we have is we have a region of high air pressure. Now, the air in front of that high pressure is still normal, unaffected, not affected yet. Now, the front of that high pressure area is called a wavefront. Now, what will happen is with that first vibration, that first pound of the drum, the drum will push in, and then it'll push out, compress the air particles, and those compressed air particles, the energy will travel through the air. And adjacent air particles will just move and continue moving away from the drum. The drum is the source of the sound. So as we can see here, what will happen is that first wave will push away or move away from the drum. And the drum itself, of course, is vibrating back and forth. And as it vibrates towards inside the drum, what it'll do is it'll take the air particles and pull them apart. And we call that rarefaction. So because the air particles are pulled apart from their normal arrangement, we end up having low pressure. So that we have low pressure here. We have that first pulse, which is radiating away from the sound source. And then ahead of that very first pulse, we have normal air pressure. So if we look at a series of pulses, and the series would be created every time the skin of the drum moves back and forth. As it moves out, it creates another one of these compressions. As it moves in, it creates another rarefaction, low pressure. So we have a series of low, high, low, high, low, high, as the sound waves radiate away from the source. Now, since we have that low, high, that simple harmonic, we can see that that's going to follow a sinusoidal pattern. And every place that we have a high pressure of air particles, that would correspond to the crest of a sine wave, and wherever we have the low pressure, the rarefaction, we would have the low pressure. And there would be a general transition here in pressure, where the middle of the rarefaction would be the lowest pressure. Here, depending on how we mark the scale, we could call that the lowest point or the negative. And where we have normal pressure, that would be represented by the equilibrium point, or the line, the midline of our sine wave. Now, some features of our wave when we're talking about this longitudinal wave. Incidentally, a longitudinal wave is also called a compression wave. And that makes sense because we're compressing the molecules or the atoms as the wave passes through the medium. The example I've been talking about here is sound traveling through air, and we know air is a gas and the particles are fluid. Sound also travels through liquids, and we know that liquid particles are closer together. And in a solid, we know that the particles have a very specific arrangement where you have one particle next to another and next to another and next to another, and their arrangement always stays the same, and that the particle in the middle isn't going to swap places. So how do we measure wavelength? Wavelength would be measured from the compression to compression. So here I've indicated that it's at the front of the compression to the front of the compression. That's how we measure wavelength in a compression wave. Frequency, when we talk about sound, we use a special word called pitch. And those of you who are familiar with music know that pitch refers to the note. You have a high note or a low note. So pitch would be how low or high the frequency is. And loudness is the same thing as amplitude. We use amplifiers for stereos, or you amplify the sound with a stereo, or your iPod, you increase the volume, which is increasing the amplitude. And that refers to how much energy the wave carries. If you have a soft sound, someone speaking in a large auditorium, what you may do is you may speak in through a microphone, and that electronics will take the sound wave, which may be very small, may have a very small amplitude, and you're pumping energy into that sound. You're not changing the pitch or the frequency of the sound, but what you're doing is you're just increasing the amplitude, and that's what we mean by making things louder or amplifying sound. Now, a little bit about our own hearing. Humans have a limited range of hearing, and it's between 20 and 20,000 hertz. We call that the audible range. Now, that's pretty much the maximum. It's true some people can hear higher than 20,000, and probably some people can hear lower than 20 hertz. But the general agreed upon range is 20 to 20,000. I've measured my hearing, and I start losing it at about 17,000. Your hearing at your age would be much better because your eardrums are more flexible. The flexibility is going to be directly related to, or the pitch, I guess, would be directly related to the flexibility of your eardrum. The more flexible it is, the larger your range of hearing is going to be. Now, if it's less than 20 hertz, we call that the infrasonic range. And sounds that are, when I say sounds, we can't hear those sounds, but there are sounds that are created below what we can hear, and those are earthquakes and thunder and volcanoes and heavy machines. We feel those sounds with the nerves in our body. We don't hear the sounds with the nerves in our ears. Now, less than 20,000, elephants and rhinos use that range of sound for their own communication. We can't hear it, but elephants can communicate at very, very large distances, 20 miles away. And the reason is, the lower the frequency, the easier it is for that to travel through space. You may know that if you're sitting in your home and somebody drives by your home, and you hear the beat of the bass of music coming from a car. You don't hear the high tones, you hear the low tones. And that energy or that frequency can actually penetrate through the walls of your home. The small waves or the high frequencies get absorbed by whatever the walls of your home are made from. Now, greater than 20,000 hertz, we call that ultrasonic range. And some examples, this is echolocation. Echolocation is also a word and same spelling but different meaning. But we pronounce this echo as in producing an echo. Echolocation, and bats can hear up to 100,000 hertz. Dolphins communicate using sounds higher than the human range of hearing. And in medicine, I'm sure you've heard about people having ultrasounds. And what we mean by that is ultrasonic imaging. And what they do is they direct sound waves into the body, and those sound waves reflect off of soft tissues. And if you capture those sound waves, you can actually paint an image using sound. Now, some additional terms. Supersonic means faster than sound. That means it's greater than 331 meters per second at 0 degrees Celsius. We'll talk about the effect of temperature on sound later. When we talk about a pure tone, we're talking about one frequency. So that's a single frequency. And a very common example of a pure tone that you encounter all the time, your telephone, your push-button telephone produces tones. The standard is that our push-button telephones has 12 buttons on it, right? 4 rows of 3. 1 through 9 plus 0 plus the pound and asterisk key. Each one of those keys has a coded sound made up of 2 pure tones. And for example, the 5 key, when you press it, there are 2 distinct tones that are produced at the same time. And that's 770 hertz and 1336 hertz. What you can do, and you can try this at home, if you take 2 touch-tone phones that are not on the same system, what you can do, for example, you can take your household phone and your cell phone. If you punch in the numbers in your household phone to produce the tone, and you hold it by the the microphone of your cell phone, you can use one phone to activate the other because it listens for the tones. The number 9 key corresponds to 852 hertz and 1477 hertz. And that's a worldwide standard. Now, the last thing we're going to talk about is the speed of sound. Speed of sound varies with temperature and with the medium or the material through which the sound travels. In air at 0 degrees Celsius, the speed of sound is 331 meters per second. We've measured that. We know that. That's a well-known number. Now, in air at other temperatures, the speed of sound is approximately equal to 331 plus 0.60 T meters per second, where T represents the temperature in degrees Celsius. So this is a formula that corrects this number. Now, the reason I say this approximates it to 2 significant digits, we get a reasonable approximation of the speed of sound. As I said, the material through which the sound travels does affect the speed of sound, and there's some complex formulas that we're not going to delve into, but I do want you to be aware that the material itself does affect the speed of sound. And that brings us to the last slide. The speed of sound is different in different materials, know that. Generally, the more elastic a material, the faster the sound will travel through it. Now, elastic, the term elastic refers to the ability of the molecules or atoms in a material to stretch and snap back to the equilibrium position. Okay, so when sound travels through air, we know that it gets compressed, and then it gets rarefied, and compressed and rarefied, compressed and rarefied. And that constitutes the wave of sound traveling as a compression wave. So elastic refers to a material's atoms or molecules' ability to snap back towards its equilibrium position. And in general, and I have to emphasize this is just a general, if you look at gases compared to liquids compared to solids, we know if we heat up a solid, it'll turn into a liquid, and if we take the liquid and that'll heat up the liquid, it'll turn into a gas. The elasticity generally increases from gas to solid. Solids are more elastic than liquids, and that's more elastic than a gas. And consequently, the speed of sound generally increases with respect to its state. So the speed of sound is very much faster in solids In a gas, in air, we're talking about 350 roughly for the speed of sound in a gas. If you look at a solid, it approaches in the thousands, much, much faster. And that's because solids have a particular arrangement, and you stretch them and they snap right back into position. Where gases are fluid, you start stretching and it just kind of goes with it.